All right, next speaker is Jonathan Heckman on compactifications of the 2-0 theory, I guess.
Oh, okay. So I'm going to tell you about geometry of 60 SCFTs. So first, let me say thanks for the chance to. First, let me thank the organizers for the chance to come here and give you a talk. Had a great time so far. So yeah, the title of my talk is Geometry of 60 SCFTs. So what I'm going to talk about is, as Carmen was mentioning, I'm going to talk about 6-dimensional superconformal field theories. And the geometry here is going to be in the context of the geometry of extra dimensions of a string compactification. And basically the idea is we're going to try and use the geometry of the extra dimensions via string compactification to learn about what kinds of CFTs we can generate in 6 dimensions and also what kind of properties we can expect, for example, with flows between different CFTs. So this is going to be based primarily on the following set of papers. Well, I didn't list any papers, but with these collaborators here, Dave Morrison, Tom Rodelius, and Kamran Vafa, as well as this longer list of collaborators. But I'm mainly going to focus on the topics connected with this collaboration. So also, we already just heard a talk on some aspects of this. I'll also refer you to Interrogator's talk in the session after this one, Park's talk, and also the Gong Show talk by Tom Rodelius. Okay, so why would you want to study 60 CFTs? We just saw some examples along those lines. There's something special about 6 dimensions, which is this is the maximum dimension in which we can expect to get a superconformal system, which conformal symmetry as well. Another interesting feature of this is that whatever the degrees of freedom making up this thing are, they seem to resist a completely particle interpretation, but it still seems to obey a lot of the rules of quantum field theory. If we want to understand more aspects of M theory, quantum theory of M fibranes, probing various geometries is governed by these kinds of superconformal theories. And as we just heard in the previous talk, compactification of these theories can lead us to insights about various lower dimensional systems. So for example, going down, say, on a circle, we can get to 5D. As we just saw on a T2, we get down to 4D. And you can play this game in many ways. And the geometry of that compactification will then show up in various ways in telling you about insights about those lower dimensional systems. So I'm not going to compactify. I'm just going to be studying in the context of 6 dimensions. What kind of things can we start looking at? So my focus is going to be on the so-called 1, 0 superconformal theories. So these are going to have conformal symmetry. They're going to have 8 real supercharges and 8 S's. And there's going to be an R symmetry, which rotates the Q's as a doublet under the SU2. And they're going to transform, the Q's are going to transform as a spinor under SO6, 2. OK, so when were these things found? First, it's been studied a lot since the 1990s. I think there wasn't really great evidence for these things existing in the first place until the 90s. And the first examples came from string theory. And it's been studied by many groups. Many of the people are in the audience right now. Basically, I haven't listed everybody, I'm sure. Around here, activity kind of died down a little bit with ADS-CFT. It's the way it is. But even now, I'd say a lot of the aspects of these things are still kind of viewed as rather mysterious. So part of what I'm going to do is try to give you a little demystification of some aspects of it. I won't obviously demystify everything. For example, I won't give you, say, a nice way to talk about self-dual tensors in a non-abelian sector or anything like that. But what I am going to do is try to tell you about some of the things we now understand, or think we understand, about how to make 60 CFTs and what kind of properties we expect for them. So in case you're jet lagged like me, I'll just tell you the results, and then I'll try to justify why we think we have these results. OK, punchline number 1. This is going to be, basically, I'm going to tell you about a systematic way of classifying 60 SCFTs. And this is going to be a top-down approach to this question. So more specifically, I'm going to tell you about how to classify 60 CFTs that are generated by compactifications of F theory. And this is in really some sense a much stronger statement than just saying it's a lot of examples. It seems to subsume all of the other known constructions of 60 SCFTs in one shot. And part of the reason for that is that F theory kind of puts all of the ingredients that you use to build an SCFT on the same geometric footing. So rather than having brains doing this and that at various pieces of a geometry, everything is going to be geometrized. Punchline number 2 is that even though this is not a bottom-up construction, so if you're skeptical, you could say, maybe there's something you cannot make. Nearly all the top-down conditions seem to have a field theory presentation. There are some gaps, which I'll mention, between the top-down and bottom-up approaches to kind of doing a classification of these theories. But at the moment, the gap is so small that I actually expect that there is a way to kind of close it down. OK, so what do these CFTs actually look like? Punchline number 3. They all have a pretty simple structure. They all look like generalized quivers. So rather than kind of the really complicated things that you can have happen in the context of 4-dimensional systems, 3-dimensional, and 2-dimensional, everything basically looks like this. It basically looks like a quiver in which you have a single spine of nodes, and then there's a little bit of decoration you can put on the left and a little bit of decoration you can put on the right. And in the middle, things are very rigid. That's what these green vertical lines are supposed to denote. In addition to that, I should also mention that the 2, 0 theories that were already mentioned in the previous talk basically correspond to a tiny nub over here in this big diagram. OK, so this is what all of these things look like. OK, punchline number 4, how you actually build these things can be phrased in terms of kind of a chemistry type analogy. Basically, everything gets built out of very small building blocks, and then those building blocks can be then used to iteratively build up bigger and bigger structures. So kind of the atoms of the picture are these kind of smaller configurations, these blue blobs. These are going to be in the geometry, various types of CP1s. And then here are also the 2, 0 theories. And then these blue blobs are going to be glued together by links or radicals that go between them. So what we're going to be seeing is that you basically build up this giant spine by taking these blue blobs and gluing them together in this way by the radicals. Punchline number 5, this is the last one, is that here's an example of something that's rather non-trivial about the classification. There are other ways of building CFTs, and you can ask, how do they fit into this list? And one of the non-trivial aspects of this is that incredibly non-trivial, non-geometric ways of building these things in other duality frames, for example, in heterotic strings, involve looking at various types of homomorphisms from, say, discrete subgroups of SU2 into E8. These correspond to specific SCFTs generated in F-theory, and they are purely geometric on that side of the correspondence. So I'll refer you to Tom Erdelius' talk for the details of that. OK, so what am I going to do in the rest of this talk? I'm going to be explaining where we got these punchlines from. And the plan is going to be as follows. First, I'm going to tell you how to build a CFT, just what are the kind of general ideas for building these things in the context of a string compactification. Then I'm going to tell you about how we go about actually classifying it, both what some of the ideas for how to present a classification scheme are, as well as kind of the evidence we think we have that this is a complete list. Then I'm going to tell you about some of the things you can do with this. Namely, if you look at the geometry of the extra dimensions, what kind of flows can you get going between different types of theories? OK, so how do you build a CFT? So let me begin with a case that has more than just the 1, 0 supersymmetry, namely the 2, 0 theories. So here are all the 2, 0 theories we know about. So if you have a problem with this being a classification of the 2, 0 theories, then you will have a problem with the rest of my talk. But this is the list, as far as I'm concerned, for the 2, 0 theories we have. So type 2b on an ADE singularity. And when you take this thing, you have a singularity at the origin, and you resolve it, you get a bouquet of 2 spheres, or CP1s. And they intersect according to a specific intersection pattern, which is dictated by the condition that you have these things be self-intersection -2, and that the resulting adjacency matrix stays positive definite. So you get all the Dinkin diagrams. By the way, the AN type one you can get from just M5 branes in flat space. OK, so I'm not really interested in the 2, 0 series. I'm interested in the ones that have less supersymmetry. So what are we going to do to start building more general types of SCFTs? What we're going to do is relax the condition that the 4 internal directions of our compactification are a Calabi-Yau. What we're actually going to demand is that we work on something called F-theory. And the idea is going to be, from my perspective, just to make type 2b, but to allow the axion dilaton to have a non-trivial profile. So the axion dilaton, I remind you, shows up as a complex structure modulus, a tau, for a corresponding elliptic curve, or T2. And the value of this tau can vary depending on what point in this 4-dimensional base, or 2 complex dimensional base, B2, we're at. So the idea, or the condition, to preserve 1, 0 supersymmetry is that this total space is a Calabi-Yau threefold. More precisely, it's going to be an elliptically fibered Calabi-Yau threefold. But we're going to allow this 1-dimensional fiber to degenerate, possibly, at points in the base. OK, so that's just a general statement about building a 1, a theory that has some 1, 0 supersymmetry. Now, how are we going to start making things that have interesting objects, namely how are we going to start making SCFTs in here? Well, what we're going to do is we're going to be looking for a way of taking a limit in our F-theory compactification such that we have some light degrees of freedom showing up that are going to be interesting and interacting. So how are we going to do that? Well, we're going to demand that in our system we have some place where we can wrap a D3 brane and let that D3 brane, the cycle it's wrapping on, collapse to 0 size. So we're going to have some CP1. And if we look at this D3 brane and what it's doing in the 6 uncompactified directions, we'll see that it looks like an effective string. And the tension of that effective string will be controlled by the volume of the CP1 wrapped by the D3 brane. OK, so the name of the game is going to be to find all the possible ways of sticking these CP1s into the base and finding ways of collapsing them down. So here's just a little more detail on those guys. We have some strings from a D3 brane. If we look at the self-intersection of the curve that's wrapped by this D3 brane, what we'll see is that that's dictating actually the kind of charge we'll have in the leftover directions. OK, now, so far all I've talked about is D3 branes in this, but one of the interesting facts about these F-theory compactifications is that sometimes other details are forced on you. It's not like you have a choice sometimes. Sometimes they're just forced on you by consistency of making a compactification in the first place. One of those conditions is that if the self-intersection gets too big, or too negative, so if it's between 3 and 12, then what you find is that actually there's always 7 branes wrapping that curve as well. This is basically because if you look at the T2 fiber, it's always degenerating over that curve. So there's always an additional 7 branes. And if we look at PQ set strings going between those 7 branes, what we find is that, indeed, there's additional particles, such as gauge fields, shooting around in the 6 dimensions. So this is always there. So this was, I think, most systematically studied recently by Dave Morrison and Waddy Taylor. OK, so what's the geometric picture for making a CFT now? Well, I'm suppressing the elliptic fiber. It would be a little too complicated to write it as well. But here's the picture of the base. We're going to have these blue blobs. These are going to be the CP1s. And what we're going to be looking for is subconfigurations of these P1s that can all collapse simultaneously to generate a conformal fixed point. So we'll get some strings from D3s wrapping the P1s, and we'll get some particles from, say, singularities in the fiber. And as I was mentioning, sometimes those singularities in the fiber are forced just because of the self-intersection. Namely, sometimes you have a choice about whether you want 7 branes to wrap the P1s, but sometimes they're just inevitably part of the geometry. OK, so as I already mentioned, to get to an SCFT, what we're going to do is start with one of our smooth bases and then start looking for ways to collapse the CP1s down. And what we need to demand is that we can simultaneously collapse all of them down to be part of the same conformal system. OK, so now let's suppose that you're at one of these conformal fixed points. How can you move away from it? There's basically 2 ways that you can see in the geometry. One is a kind of Higgs branch move or complex structure deformation. In stringy terms, you might view this as a brane recombination operation. You'll have 7 branes, which have certain gauge symmetries. And by activating operators stuck at the intersection point, you can cause a recombination. You can also consider a configuration where you take one of those curves in the base that was collapsing to 0 size and instead decompactify it. So in pictures, it corresponds to turning a circle into a square. So in the base, that's just this scalar deformation to large volumes. OK, so these are the 2 deformations. And basically, what I'm going to do is be characterizing the ways of building these things by working in the limit where we actually allow the P1s to be of some finite size. And then we're going to start piecing those together to see what kinds of Calabi-Yau geometries can actually be generated. So how do you build one of these geometries in the first place? OK, so it basically consists of gluing together a bunch of smaller building blocks. And the basic glue that holds together the building blocks is the curve that has a self-intersection -1, which I've put here in this blue dot in the middle. And then to the left and the right, we have these other blocks that are going to be glued together. And the basic condition for gluing these things together properly is that if we look at the gauge symmetry on the left and the right, the product has to sit inside of E8. So what are these building blocks? Here they are. They consist of something that was classified by Dave Morrison and Waddy Taylor, 2012. Got cut off a little. It's these configurations of curves. Again, these are blue blobs, and this N here indicates the self-intersection of the curve. And all of these cases have the property that there's a gauge symmetry or i.e. some 7 branes wrapping the corresponding curves. Additionally, there are these 2, 0 theories. And finally, there is the glue that's holding together all the rest of the blocks, which is this famous so-called E-string theory. The dual presentation of this thing is in terms of a M5 brane next to a Horjava-Witten 9 brane E8 wall. And this theory enjoys an E8 flavor symmetry. By the way, the reason why I was saying this gluing condition with G left times G right can be thought of is basically taking that flavor symmetry and gauging a product subalgebra. OK, so here are some examples. Kamran already mentioned some of these, so I won't spend too long. Here are some more examples. You can make things that look like E-type quivers. These are a little bit harder to think about in terms of a Lagrangian description. But you can nevertheless write down a diagram to write down precisely what's happening in the geometry in the same vein. So the point is that here you have this E6 on the left and the right. And in between, you have some glue with this -1 curve hooked up to this -3 and so on. And the glue can get itself into some bigger blob like this. So for example, here you have about 11 curves, which are suspended in between the 2 E8s. Now, one of the interesting things about these guys is that the link itself is also an SCFT. And here I've just shown you a little bit more of detail about what that SCFT looks like. OK, so what I've done so far is just presented you with a list of examples, or how you might start trying to build some examples of SCFTs in the context of F-theory compactifications. What I'm now going to do is tell you about how to classify all the possible ways of taking F-theory, compactifying it, and making a 6D SCFT. So in particular, I want to explain the fact that we got this spine, this generalized quiver that had a single spine of nodes. OK, so that's what I'm going to do next. OK, so it's going to be a top-down approach. And the idea is going to be, can we actually enumerate all the possible theories? And the answer is yes. So what's the evidence that we have this? Basically, it's because in F-theory, everything is on the same footing. It's all going to be geometry. And the other piece of evidence for this is that it seems to subsume all of the other ways that we know how to build theories. So this includes all the classical theories, classical quivers. I'll talk about those in a second, as well as more non-trivial examples involving, say, small instantons with various pieces of boundary data that are pretty tricky to completely characterize in purely heterotic terms, but are pretty straightforward in F-theory terms. So here are the quivers. Here are some examples of quivers. There's things like this with just a bunch of SUNs. Kamran already talked about this case. But you can also have things where you have the SUN replaced by E8. And this link here is itself now an SCFT. It's no longer just a weakly coupled matter. As a more non-trivial example, you have small instantons. So basically, you have instantons and various boundary conditions for how the instanton behaves off at infinity get related to homomorphisms from discrete subgroups of SU2 into E8. That in turn corresponds to specific Calabi-Yaos. And there's an algorithm for going between these two. And what seems to be the case is that these homomorphisms correspond to specific RG flow classes in which the flavor symmetries are preserved along the flow. OK, so now these are the kind of the pieces of evidence that we have that it seems to be covering everything that we previously knew about, as well as many, many more. What's the strategy for finding these things and for classifying these things? What we're going to do is we're going to first split the problem up using the F-theory organization of the problem. Basically, we're going to look for all possible bases where we can try and collapse the P1s down to 0 size. And then we're going to look for all possible ways of wrapping 7 branes over a given base. So we're going to split the classification up into 2 pieces. Now, the first piece is actually, in some sense, the more combinatorially challenging piece. So I'll focus my attention there. Here's some useful terminology. You can take these curves of various self-intersections and split them according to whether the minimal 7-brane gauge symmetry is of D or E type algebra, or whether it's of a non-DE type. So this will be these are going to be kind of DE type curves, and these are going to be the ones that don't have that. So for example, a -5 curve carries, say, an F4 gauge symmetry minimally. OK, so that's the first piece of terminology. Second piece of terminology, I'm going to denote the DE type curves by a blue circle like this. And I'm going to indicate that minimal gauge group like this. And then a link is going to be something that's connecting up 2 of these blobs by everything that's not a DE type curve. So anything that is not DE type. So in this example, this notation was basically invented because I'm very lazy. You have 11 curves here, and you can replace that by this line. Same data. Okay, so the idea here is that we're going to be looking for all possible ways of taking these blue blobs and hooking them up together via these links. Okay, so the big surprise when you do this is how constraining it is to actually build an SCFT at all. This is what these things look like. Okay, so you find that they have a very simple structure. You can only hook these blue blobs up together in a single linear chain. If you try to make something where they hook up into a more complicated topology, you violate the condition that you can collapse all the curves simultaneously. Moreover, if you look at the gauge groups associated with these guys, they form a nested sequence of containment relations. Thanks. Okay, so in addition to that, these vertical lines tell you a little bit more about where you're actually allowed to kind of supplement the minimal description by something a little more non-minimal. So basically, in the middle of one of these quivers, everything is basically very rigid. You're kind of stuck with the minimal type of thing you can do. On the left and on the right, however, it is possible to consider various types of decorations. That's what these little spokes here, here, and here correspond to. And these spokes here, the IL, IM, and IN, correspond to a very specific configuration of curves. Looks like a sequence of 1 and a bunch of 2s. This thing is kind of the L instanton, corresponds to a theory of L small instantons if viewed in isolation. So you take this thing and you kind of pin it on to some place. But you can only pin it on in specific locations in the quiver. Okay, so that's kind of the core of the classification, because it kind of tells you what are the possible bases that you could have in the first place. Then there's the rest of it, which is to then say, given one of these bases, how many different fibers can you actually put over it? Namely, how are the possible ways of actually wrapping additional 7-branes over this? So that's also been classified. And all the possible links as well. Okay, so that's basically the sense in which we have kind of a top-down classification. We've listed all the possible ways of generating a base, all the possible ways of wrapping 7-branes over that, i.e. making the elliptic fiber possibly more singular. And yeah, that seems to cover everything that we knew how to build CFTs for in the previous times, as well as a huge amount more. Okay, and it's pretty systematic. That's the other thing I want to stress. Now, one thing is that what I've done so far is focused on kind of a top-down construction. And I mentioned at the beginning that there were still a few gaps between the kind of what the field theory says and what the F theory is saying. And here's an example of one of these. Basically, it's an SO8 gauge theory. It has an appropriate number of fields and various spinor representations as well as a vector. And it's kind of an outlier. This thing actually cannot be built in the context of F theory. And one of the ways of seeing this, one symptom of this, is that when you try to weakly gauge some of the flavor symmetries associated to the system, you find that it actually doesn't, it cannot be done without kind of violating the conditions of building a Calabi-Yau threefold. So I suspect actually that this theory, in field theory terms, is kind of sick. The only condition I impose to write this one down is just kind of a condition under continuous anomalies. But I suspect that there's something subtle about the global structure of the gauge groups, which is throwing this out. But I leave that for future work as a possible outlier. Okay, so this is the kind of sense in which things are really close. I'm only mentioning this one because it's the outlier, but this is almost the only outlier that we have. Everything else is basically matching up with what you'd expect. Okay, so RG flows. So that's going to be the last thing I'm going to talk about. So I already mentioned there's two kind of deformations you can do. So given one of these Calabi-Yau geometries, there's kind of two generic ways of performing a flow. One is a kind of brane recombination move, and one is a move where you kind of ungauge or turn circles into squares. And what you'd like to know is which one of these deformations actually triggers a flow to a new conformal fixed point, and which one just leaves you at the original conformal fixed point. So this is actually a rather challenging math question if you just ask it directly in the terms I just said. Namely, what you want to know is what counts as a good deformation, namely one that will trigger you to a new CFT. So here's kind of something you can spot by eye. This is clearly going to deform the geometry in a nice way. But this one probably will not do anything too interesting because it's such a high degree deformation. Now, this is an obvious one to spot. But when we start writing down these more complicated Calabi-Yau geometries, it's pretty hard to just spot by eye whether this thing is going to be a normalizable deformation or not. So as a physics shortcut, you can calculate an anomaly polynomial associated to these theories. You can check whether if you take two theories and you compare them, whether the thing is actually going to generate a difference. If there is no difference, that's reasonable evidence that you didn't actually do anything. But if there is a difference in the values of the anomaly polynomial, then indeed, okay, there's a discrepancy, and that points to the idea of a flow. So I think Ken will talk more about this, but the basic idea is switching on an R symmetry and tangent bundle field strength, and then tracking the behavior of these 4 coefficients. These are just some formal characteristic classes, and the anomaly polynomial here is a formal 8 form. OK, so here's an example of a flow where you see that. I'm almost out of time, so I'll quickly get to the rest of it. At the bottom, what these things look like is basically theories that are either the 2,0 theories or theories that don't have any complex structure moduli. The last thing I'll mention, I'll go extremely fast on this, is that since we have what looks to be a very big list, a very complete list, is we can also start looking at numerical quantities that are decreasing as you go from ultraviolet to infrared. And you might try just by brute force sweeping over all the different choices. So what we did in a paper with Tom, which will hopefully be out today, tomorrow, I can't keep track because it's India. OK, so there'll be some linear combinations of the anomaly polycoefficients. And what you find is that actually there's huge classes of things that are all decreasing as you go from the UV to the IR. And actually, it's usually the simplest theories which are generating the tightest bounds on what is allowed to be monotonic. So using a computer sweep, you can find that there's actually big sets of things where everything seems to work. And this value here, MA, is one that Ken is going to talk about here. And it's indeed consistent with all the flows that we looked at. So it seems to be a little bit different from the case of, say, 4 dimensions or 2 dimensions, where you kind of nail down an A. OK, conclusions. What did I tell you about? I told you about 60 CFTs and how you can basically view them all as generalized quivers. And moreover, what I told you about is the work that was done on this classification, at least for these F-theory compactifications. And finally, I also told you about kind of the evidence we have for now looking at a computer sweep over these numerical quantities associated with the anomaly polynomial coefficients. I think the next thing up in this kind of story is to kind of use the fact that all of these theories kind of look the same. They all look like generalized quivers, to start extracting general lessons about all the 60 CFTs in one shot from the fact that they all kind of have very similar looking features. OK, that's it for me. So thank you.
Thank you very much. Questions or comments? Edward?
When you talk about gauge groups,
Yes.
that really refers to a deformation away from criticality to where you can talk about a gauge group?
That's right. So my discussion was in terms of moving on to the tensor branch, so activating the scalar in the same supersymmetric multiplet that contained the 2-form potential. And then on that branch is then where we're actually giving the gauge group description. Indeed, once we go to the conformal fixed point, the gauge theory description is not very useful at all. Yeah.
Any further questions or comments? If not, then let's thank Jonathan again.
Oh, sure.
Was there one?
Sure, I said it.
Oh, sure. Yeah.
Could one hope to use the conformal bootstrap to verify your classification 1.0?
I hope so. Well, I think actually the more reasonable thing to look for is I'd actually like to know more about the spectrum of operators in these systems and know more about the scaling dimensions. So I think, I'm not an expert on conformal bootstrap. I've been asking them about what you can say about 1,0 theories. I hope the answer is yes. Yeah. Oh, I should add one more thing. I expect that actually it's easier to say some things about the 1,0 theories than it is about these 2,0 theories. And the reason is because they have a big flavor symmetry. So precisely, if you look at, say, M2 branes, right, you lost some supersymmetry when you looked at M2 branes probing various orbifolds, but you gained some, some additional structures, which helped you understand some properties. I expect something similar like that probably helps you out in the case of the 1,0 compared to the 2,0.
I think we have to move on, so let's thank Jonathan again.
Thanks. Okay.